Hello and welcome to the accadis video series on economics. Today we will turn to an application of our models. We will try to estimate a demand curve and calculate the price elasticity of demand based on sales data. Setting prices is one of the main decisions a company is making in its marketing strategy. Of course, any company would like to set the price as high as possible in order to increase the revenue, price times quantity sold, of course. But as you all know, there is a problem with that. The higher the price, the more people will try to escape the market since they're not willing to pay this much. So a price increase might very well lead to a lower revenue when demand falls and lower quantities are being sold. The demand curve was our way to model this relationship. As you remember, it slopes downward. The higher the price, the lower demand, since people with a lower willingness to pay leave the market and don't buy the product. And how strong this relationship is determined by the so-called price elasticity of demand. So how much does demand change in percent if the price increases by 1%? Some products have inelastic demand. Our example was gasoline with a demand elasticity of minus 0.35. That's below 1 in absolute terms. So a 1% price increase will lead to a reduction of demand by less than 1%. And of course, that's good news for companies that are selling this product. They can increase the price without causing a strong reduction in demand. And this means their revenues might increase when they increase the price. If demand is elastic, however, this might not be the case. Remember the price elasticity of soft drinks, which was estimated at minus 1.6. A price increase of 1% will there cause demand to fall by more than 1%. Now that's all good to know for a company that tries to set up its pricing strategy. There is one major problem, however, of course. All of this so far is just a theoretical model. There's no data available that directly shows the willingness to pay or gives us the price elasticity directly. We need to find the appropriate demand curve for the product that we're looking at by ourselves. The first step here is to think about the determinants of the price elasticity for the specific product. So we want to answer the question whether or not the ability to escape the market is high or low. For a company, it makes sense to focus on three of the determinants that we know. The first one, are substitutes available or not? The second, is the product a necessity or a luxury good? And thirdly, does the purchase of the product represent a small or large share of the typical customer's budget? These factors will broadly determine whether or not you may expect a high or a low elasticity for the product that you're analyzing. Let's practice this with our two examples. When you are a company that is selling soft drinks, you clearly face a lot of competition from other products since there are many substitutes available. For example, water, tea, or whatever. Companies that sell gasoline do not have this problem. There are very few substitutes available, especially in the short run. Furthermore, gasoline is clearly a necessity since most people rely on their car to drive to work, school, or to a supermarket or wherever they need to go, while soft drinks are more of a case of a product that lies somewhere in between necessity and luxury goods. Not everybody needs to have a soft drink every day. Some people do, but not everyone. So even though the share of the budget, rather low for soft drinks, a little higher for gasoline, reduces this effect a little bit, the implication of this example is clear. For gasoline, you have a low ability to escape the market, while for soft drinks it's rather high. So we can expect inelastic demand for gasoline and rather elastic demand for soft drinks. So in general, the estimates we discussed make sense, but that is not enough for us. We want a concrete estimate of the price elasticity of demand if we want to decide on a pricing strategy. Of course, the figures we discussed were estimated by professional economists with lots of data and quite complicated statistical methods. But even with less data and simpler models, we can get a pretty good first estimate of elasticity that we can then use to inform our pricing decisions. In order to understand how, let's turn to a simple example. Imagine you're running a stall at the Christmas market and you want to determine the best possible price for your Glühwein. It would certainly be highly interesting to know the price elasticity of demand so that you can find the highest possible price that will not scare away too many customers. So what you want to do is estimate a demand curve. To obtain the necessary data for this, Let's say you conducted a small experiment with your Glühwein stall. Every evening at 8 p.m. there was a happy hour special offer, 5 Glühwein at a reduced price. And you tried every whole euro price between 14 and 20 euros and recorded the resulting sales numbers. The results of this experiment looked as follows. On the x-axis is the price and on the y-axis is the quantity purchased, so the sales. We now want a function that fits this data. Let's start with a linear function. From your statistics course, you know how to get such a function based on this scatter plot. We simply use a simple linear regression to estimate it. Let's do this in Excel. We represent the data in a scatter plot and just add the trend line. Then we let Excel show us the function for this. It is y equals 100 minus 4x. And just like that, we have a demand curve for our product. Sales, so quantity, equals 100 minus 4 times the price. Here we can just plug in prices to get an estimate of the sold units at that price. For example, at a hypothetical price of 22 euros, we can expect sales of 12 Glühwein specials. By the way, this function is flipped, as you might call it. Usually we used P on the y-axis and Q on the x-axis to represent the demand curve. But for calculating elasticities, as you will see, it's easier to do it this way around. It does not matter anyway. We could just transform this function easily into a function that is P of Q. Just add P on both sides, divide by 4, and we have P equals 25 minus 0.25Q. This is the exact same function as the one we estimated, just flipped. But plugging in values is not all we can do with this demand curve. We can use this function to estimate the price elasticity of demand. And in order to understand how, we need a little math, so we can go back to our good old board. Welcome to the board. So we have our demand curve. We have a function for that, which is just Q of P. And now we, let's say, start at a price of P0, and then we change this price by some value, which we call now delta P, which will of course then give us a new price of P1. And this will lead to a change of the quantity, right? We have the quantity Q0, let's say, where we started, and then we change by delta Q, which is probably negative, and then we will arrive at Q1. What we want now is the change in percent. No longer just the absolute change, which would be our delta, but we want the change in percent. So we take delta P and divide that by P, which will give us the percentage change of the price, and we take delta Q divided by Q, which will give us the relative change, the percentage change of the quantity. And our elasticity of demand is now simply these percentage changes divided by each other. So the percentage change of the quantity divided by the percentage change of the price will give us what we want. It will give us the percentage change of the quantity when the price is changing by 1%. So very easily we can just say, okay, we want to have delta Q over Q divided by delta P over P, and this is going to give us the elasticity of demand. We can change that around a little bit, make it look a little nicer. This is delta Q times P over Q times delta P, and then we can rearrange that one last time. P over Q times delta Q over delta P, and this should look familiar from your math class. You know that this is for infinitely small changes, yes, but this is the derivative, the Ableitung in German, of Q of P. So it's just the derivative, the Ableitung of our demand curve. And then we have a very easy formula for the price elasticity of demand. It's P divided by Q, and now there of course we can plug in our demand curve, Q of P, times the derivative of that. So when we now take our function that we have calculated in our example, which was Q of P is equal to 100 minus 4P. First of all, we know of course that the derivative there, the Ableitung, is minus 4, and then we can just calculate the elasticity of demand by taking P, dividing by Q of P, so dividing by 100 minus 4P, and multiplying that by minus 4, which will then give us minus 4p over 100 minus 4p. We can make this look even nicer when we divide everything by minus 4, which will then give us p over p minus 25, and that is our estimate for the price elasticity of demand, which, as you can see, of course, now is a function of the price. So now we have our price elasticity of demand based on the linear function Excel gave us. The elasticity of demand is equal to p divided by p minus 25. As you see, this is now a function of the price. It's not really a fixed number as it was before. Let's plug in some values. If the price is 20, elasticity will be 20 divided by 20 minus 25, so it's minus 4. So at this high price range, elasticity will also be high. If we increase the price even more, we will lose lots of customers. For a 1% price increase here, we lose 4% of our customers. If the price was low previously, however, it will be different. Let's plug in a price of 10. Then we get an elasticity of 10 over 10 minus 25, which is minus 0.66. So here we would only lose 0.66% of our customers when we increase the price by 1%. So you see that our linear demand curve is implicitly making an assumption. We see that the price elasticity depends on how high the price was before. But that is not necessarily what we want. It would be better to arrive at a constant value for elasticity, just as the economists did for soft drinks and gasoline that we have looked at before. Luckily, there is a simple way to do this. To understand how, we need to go back to the board for one last time. Welcome back to the board. So far, we assumed Q of P to be a linear function. So it was just Q of P equaling A minus B times P. And we found values for those. We estimated them 104. But why not take a nonlinear function? We could just as easily say our demand curve is now A times P to the power of B. Just another form, and we need to find values for A and B. What we want to find out first, though, is what's going to be the elasticity of demand in this function. And as you remember, you get the elasticity of demand by taking P over Q of P over the function times the derivative, the Ableitung of that function. So the derivative here of our function A times P to the power of B is simply B times A times P to the power of B minus 1. So let's calculate that. We have P over A times P to the power of B times the derivative times B times A times P to the power of B minus 1. Now, let's simplify this and you will see that something nice is happening. So, we have B times A times P to the power of B minus 1 times P divided by A times P to the power of B. Now, you might remember the Potenzregel from your math class. If you have x to the power of something to the power of A times x to the power of something else, B, it is simplified as x to the power of A plus B. And we can use this here. We can say, okay, this is B times A. Now let's see what happens to P to the power of B minus 1 when we multiply that by, well, 1. Simply, it's going to become P to the power of B, because this is B minus 1 plus 1 is just simply B. So we have here B times A times P to the power of B divided by A times P to the power of B, which of course cancels out. And then you see that the elasticity of demand of such a function is the exponent. It's just B. So if you see a function which looks like this, A times P to the power of B, you can simply read the elasticity of demand from this exponent. So when we assume such a nonlinear function, we get an estimate for a constant elasticity. And luckily, we already know how to estimate this kind of function. Let's go back to Excel. We just need to go back to the scatter plot with the trend line and tell Excel that we now want a nonlinear function, like the one we just used. So we tell Excel that we want a trend line estimated with the option power, which would be Potenz in German. You know from your statistics course what happened in the background as Excel estimates the function with logarithms. And this now gives us the following function for the demand curve. Sales equals 11,211 times the price to the power of minus 2.089. So from this, we can directly take the estimate for the price elasticity. Here it is, minus 2.089. So demand for our Glühwein is rather elastic. A price increase of 1% reduces demand by round about 2%. This, of course, has implications for our pricing strategy. If we increase the price, we will scare away many customers. Makes sense, since there are lots of substitutes for Glühwein, and even around Christmas time, it's not really a necessity for the customers. Hence, the ability to escape the market and price elasticity are probably rather high. Of course, doing this just gives us a first rough estimate of elasticity. Many other factors may have played a role when the sales data was collected, and to get a better and more correct estimate you would need more data and a little more advanced statistical techniques. But nonetheless, this procedure provides us a good way to at least get an idea of how high elasticity probably is, which will surely help us with the pricing strategies.